what I'm trying to do here is to connect paleogeography specialists, paleoenvironmentalists, deep time paleogeographers with a kind of pressing problem in essentially climate change mitigation. So very different to Delphine, who's looking at past climates. What I'm looking at is the future climate and what geology could do about it. And so my talk is really to try and get you clever people thinking about a particular problem, which is a problem, which could hold up some of the important ways that we can try to combat sort of emissions and climate change. So I'm going to just talk about some introductory stuff. Then I'm going to give you some CCS basics. So I really apologize to you if it's too simple or too difficult, but I'm not sure what knowledge people have on the talk about carbon capture and storage. Then something about what I think paleogeographers, particularly deep time paleogeographers, could actually do to help in some of the problems that we have in CCS, and then some conclusion. So it's more of a kind of talk where I'm trying to connect two communities, really, which are very, very different and very separate and very, very much apart. And the odd thing about me is that I kind of sit in both worlds. So I have a CCS expertise. I was chief scientist of the British Geological Survey for a very long time. I managed and led many CCS and geoenergy projects and did a lot of sort of communication of science, lots of books on science. One of my books is on carbon capture and storage. It's really the only introductory book on carbon capture and storage. But at the same time, I was having a kind of shadow career in palynology, stratigraphy, and Earth events, because I'm a palynologist. So interested in the Permian, lots of papers, lots of professorships. I was the chief editor of the Review of Paleobotany and Palynology for 12 years. So what's odd about me is that, apart from many other things, I have an interest in both kind of the large-scale geoenergy problems that the world has and the stratigraphy and Earth events that the world so nicely demonstrates. So this is where I come at it, and what I'm trying to do is kind of join people together in this talk. So first of all, CCS and climate change. If you're not aware of it, then a quick thing to read about the geological carbon sequestration is this new Royal Society report that came out either this year or late last year. And it's really important. CCS, if you're not aware of it, is part of the climate mitigation programs of most developed and many developing countries. It's seen by most scientists as absolutely essential for the Paris commitment. Presently, we sequestrate or store artificially, geologically, only about 40 million tons of CO2 per year. That's all we do. And given that an average power station produces 10 million tons, that's not very much. And in order to get to a 1.5 degree, it's thought that about 7 to 8 gigatons of CO2 storage per year is needed by 2050. And something like a cumulative storage of 350 to 1200 gigatons by 2100, if we want to get to 1.5 degrees C. And we'll be injecting maybe 1 to 2 million tons per year. So there could be thousands CO2 projects by 2050. So the chances are lots of geologists will be doing this, an awful lot. In fact, it could be, an alternative to the oil and gas the business. So this is, if it's going to happen, it's going to be big. So some very, very basic CCS 101 for everybody. So I really apologize if you already know a lot about this. So first of all, CO2 is going to be sequestrated and sequestered, stored in basically sandstone or carbonate rocks, 1 to 2.5 kilometers deep, pretty high porosity, quite large reservoir layers. And the important thing to realize is it's going to be stored as a supercritical fluid. So again, I know I'm talking to people who don't normally discuss this kind of thing, but just so you know, so as a dense phase, it occupies a tiny amount of its volume that it occupies at normal standard temperature and pressure, STP. So it's less than, much less than 1%. So it makes sense to store it in a supercritical form, sequester it in supercritical form, and that normally happens below about 800. So storage and time. So how it's stored, how it's sequestered, kind of depends on how long it's put down or how long it stays down, say a reservoir like a sandstone or carbonate. So at the start, it will be free CO2, but it will be in the supercritical form, a buoyant fluid in the subsurface, rather like pore fluid. And it will tend to be trapped rather like a trap or an oil and gas trap, so trapped under an impermeable layer. But over time, we know that CO2 will dissolve in pore fluid in water. And that essentially causes a slightly denser fluid, which actually sinks through the reservoir. Again, I'll show you some of this graphically. Finally, over a very long time, CO2 could dissolve, could actually react with material, rock, material, mineral in the rock. You see some examples here of CO2, which has actually structurally turned into a carbonate mineral within a sandstone reservoir. Mineral crystals. So essentially, we don't really know how long it takes. It depends on the reservoir, but as you go this way, it gets a bit safer because the more likely the CO2 is to not be able to get out of the reservoir because it's becoming fluid and then it's solid. So I'll show you why this is important. So again, I hesitate to show you something so simple, but really the physical trapping of CO2, you want to trap it in a rock structure like this, an anticline. And you can see a lovely anticline. Basically, you drill a hole in the anticline. Obviously, you won't be able to see it. The depth will be quite high because it has to be supercritical. You drill a hole. You hope you have a seal. So, in other words, an impermeable layer that stops the fluid coming up. And then you squirt, you inject CO2. And essentially, what you're doing is pushing the pore fluid out of the way. So the pore fluid, usually water, saline water, is pushed out of the way by the CO2. And the CO2 occupies the space. So that's really the simple principle of physical trapping. It's pretty simple. It's creating a sequestered mass of CO2 way down in the deep subsurface. But there's some things you need to know before I continue. So first of all, for a physical trap, you have to think about what system you're doing. So here's a lovely sandstone layer. Let's say it's this pink sandstone layer with some faults. This is in Utah. And let's say you drill a hole into it and you want to sequester your carbon dioxide in dense veins. And let's say there are two faults which are sealing faults. In other words, they prevent CO2 from moving across them. And let's say you have a seal above and below. Imagine some of you are despairing at this point. Why is he talking about this? But it'll become clearer in a minute why your expertise in understanding sedimentary sequencing could help in helping us inject better and store CO2 better. So basically, as you inject your CO2, there it is, you're going to push the pore fluid out of the way because you're occupying the space with CO2. So the point is, if you do that in a closed pressure system like this, you're obviously going to increase the pressure inside this box. And if you increase it too much, in other words, if you increase it up to the level of lithostatic pressure, so the pressure of the rock above, you could crack the rock. You crack the rock, then you'll lose the CO2 and it will be all pointless. So you have to understand about pressure. If you don't understand pressure, then it's not a great idea to start injecting CO2. And again, bear with me here. If you don't know what I'm talking about, you'll soon understand. Let's take an example of physical trapping in a big layer of rock. This is a layer, Bunter sandstone, offshore North Sea. You see this red area here. The red area is shown in this dotted line. This is the Triassic layer, which would be used in the UK in the future for storing CO2. Quite well understood. It has the layer is sometimes deep, i.e. blue, shallow, i.e. red. Sometimes it comes close to the seabed. So in a few of these high locations, the Bunter sandstone is very close to the seabed. So if we take that layer and pretend in this simulation that we're going to inject CO2, we inject it in 12 places, in 12 trap structures where we think the CO2 will be held. It's just a simulation. And we're injecting for 3 power stations worth, that's 30 million tons per year for 15 years. So this is the CO2 saturation of that 15 years. Saturation just means the amount of the pore space which is occupied by CO2. And you can see it's quite high and it's quite low around the edges. But the key thing to note is it's an enormous amount of space. You could easily fit 3 power stations in there after 5 years, after 50 years. So it looks like a good area, a good space. If you take an open system, so let's assume that there are no big faults, so the structures only confine the CO2 at the top, not sideways, then if you pump it up with this CO2, actually the percentage of lithostatic pressure that you reach is about 80% in some places, which is kind of worrying, but generally it's low, which means that it's not going to cause too much trouble. Where it is high, it may be allowing CO2 to get into, or it may push, not CO2, but pore fluid in the reservoir into the seabed. But that actually might help to relieve pressure. In a closed system where there are faults, you can see that the lithostatic pressure is reached in more places. And that's just simply because faults might be stopping the CO2 from getting out and also causing the pore fluid not to be able to move sideways. In other words, increasing the pressure. So again, bear with me. So why would I be interested in talking to a lot of paleogeographers and paleoenvironment specialists about this? Well, the reason is fairly simple. The reason is because if we take this pressure system again, if we're injecting here, we want to know about porosity and permeability of the bulk formation. We'd like to know how porous and permeable these rocks are on a really large scale. Because remember, we're talking about maybe 5,000 CO2 injection projects by 2050. We also need to know about small-scale heterogeneity. Small-scale heterogeneity. So in other words, heterogeneity which might impede CO2 flow through the rock at a subseismic scale, where you can't see it on seismic. You choose a rock, start squirting and injecting CO2, it doesn't move because, or it doesn't get in the rock because there are heterogeneities, mainly like mudstone back, thin layers which have primary origin, which are not allowing the CO2 to move within the rock, and therefore increasing the pressure, making CO2 injection more difficult. So let's look at a famous CO2 injection place. This is the most famous and most successful CO2 injection site in the world. It started in 1996. They've been injecting 1 million tons of carbon dioxide into this formation here, the Sierra Sand, since 1996. And 25 million tons of carbon dioxide, supercritical form, dense phase in this rock. Now, when they started doing it, this is the layer itself. This is the subsurface rock of the Sierra Formation. This is the injection. What they found after a number of years was that although seismically you couldn't see it, this sandstone contained lots of thin shale layers. They were too thin to see on seismic. So it caused a lot of worry because people thought, if we're trying to inject, maybe these thin shale layers are going to get in the way of the carbon and prevent it moving as easily as we'd like it to. And what they found was when they modeled it, when they used repeat seismic surveys tuned to pick up carbon dioxide, what they were able to see was this. So this is the upper level of this, that's the sea, on the base of the sea. This is the bottom of the reservoir. The injection point is somewhere down here. These red-gray layers are layers of supercritical CO2. And these have collected underneath those shale layers that I showed. So what they've shown is that the shale layers are impeding the upward movement of the CO2. It's a buoyant fluid, but it's not moving as quickly as you'd expect because it's being held up by the shale layers. And it's not reaching the top as quickly as they thought. At first, they worried about this because they thought it might mean you couldn't get the CO2 in there. But in fact, it went in there. And they began to realize that actually it has a value because it's actually slowing the CO2 down, making it less of a burden for the seal to contain, but also allowing CO2 to dissolve because it's being held back by the flow by these shale layers. You can see that again there. This shows you the same thing, but on a slightly different tack. These are the layers of CO2, or high saturation layers of CO2, underneath these thin shale. This is the base of the seal here. If we move through this, you can see those stripes of red and blue. This is the bottom of the seal. You can see the CO2 arriving at the base of the seal, carbon dioxide arriving at the base of the seal, about a year after the beginning of injection. And this is a picture showing the same size, showing the development of the CO2 collector. So what's interesting is that these low permeability mudstone layers promote solubility trend, leaving the overlying seal to do less work. But it also could reduce the volume that could be injected. So the mudstone extent and thickness is really important. In other words, we need to understand these reservoirs. Some paleogeographers, some fasci specialists and sedimentologists are beginning to think about this. Not many people are doing this. But essentially, as a group at BGS in the UK, a guy called Andy Newell, who's working on the Otter sandstone, which is a mudstone, Triassic sandstone mudstone complex, which is a target for CO2 offshore in the UK. What they're essentially trying to do is build models of these rocks and to try and predict what that might mean for CO2 injection. So they start with a laser scan, build a sort of simple image like that, a static model, and then they build a model with essentially porosity and permeability, and then they do flow injection, flow simulation. So this is a gas saturation flow simulation. But I hope you can see here that essentially what you're looking at is the primary controls on the form of this sedimentary rock and how those might be affecting the ability of the rock to store CO2. Bear in mind, as I said, we may need 5,000 projects. So at this level, subsidence, I think paleogeography, sedimentology could be very useful in understanding reservoirs. So can you, asking you as a group, can you identify, predict, and forward model the fascies that we're talking about? What about the big scale? In the big scale, the basin scale, permeability prediction and forward modeling at big scale. So this is, I note that Mike Simmons is on the call. So this is a paper by Halliburton, Gravestock. So what they were looking at here was using, at this really large scale, so you can see the scale here at about 50 miles, the ability to take data, take paleogeography, paleoenvironmental, fascies data, often from oil and gas exploration. For example, thickness of a formation, porosity of formation, the net to gross, so and that's petroleum sort of jargon for the amount of sand to mud, how porous and permeable. And using that, essentially using various sort of artificial intelligence methods to come up with prospective storage at a very large scale. So not detailed enough for you to really decide where you're going to look at injecting CO2, but where you might start thinking about it, and you might start doing detailed geological analysis. So really, again, this is from the same paper. Can you convert your paleogeography, work that you do as a group of scientists that Sabin does and others, where you think about basins, think about what the controls are on basins, on controls are on sedimentary layers in basins. Again, Halliburton, famous group working on this. There are a number of forward stratigraphic model groups who essentially build up basins artificially through all their topographic process systems, which essentially enables you to create a basin. But you can use the same techniques perhaps to produce thickness, porosity, net gross, and therefore prospective storage. And again, you may say, well, this is not what I do, but I think it's something that if people in the paleogeography community put their minds to it, it's something that could be quite useful. So my summary on this, sort of basically a pitch to you, my sort of attempt to persuade you, is that there are significant uncertainties in the CCS world about heterogeneity at a meter scale, it's a small scale, less than 10 meters, which are below seismic resolution. You can't see them on seismic, and yet they could have a strong influence over the ability to inject the CO2. Either it might make it harder to inject, in which case we spend millions of pounds drilling holes and finding they don't work, or you might find that you simply can't get the CO2 in there. But also it could be that the heterogeneity helps you, as I showed you before, where shale layers actually prevent the CO2 from moving too quickly, and therefore allow it to start dissolving or actually reacting to formation, which is good because it contains the CO2 better. That scale, but also the bigger scale. Can the maps, the models that you produce, can you use them to develop understanding of permeability, therefore, say, overall, a first pass idea of the potential for CO2 storage at 100 kilometer square scale, as the previous paper showed. So the conclusions, I've gone through that very fast. I'm sorry if you didn't get the basics of CO2 sequestration, but essentially CO2 sequestration requires great knowledge of sedimentary sequences, e.g. the balance between injectivity and at least two areas which I think sedimentologists, paleogeography specialists, environmental specialists can contribute to are the understanding of the generation through primary controls of the small-scale heterogeneity. And secondly, the ability to produce high-level screening, perhaps at 100 kilometer level, for particularly saline aquifers, which are a big target for CO2 sequestration. And I think this is a really big opportunity for your science. I know they look a bit odd to you at the moment, but as I keep saying, this sort of study could be, the basis for understanding many thousands of CO2 injection projects by 2050. Okay, so that's my mic. This book that I mentioned, Returning Carbon to Nature, I've just negotiated the writing of a second edition. So I'm writing a second edition for Elsevier in the next year and a half. So also, if you're interested, the DDE program is looking at this particularly and has a kind of developing CCS program. So through this DDE paleogeography group that I'm studying these, this is something I think we could do if we could get the right scientists together. So CCS people don't often meet with paleogeographers and paleontologists, but I really think they should start doing that. So thank you very much.